Abstract. The research studied the effect of the steam injection process with naphtha and catalyst on the corrosion of carbon steel API P110. The discontinuous gravimetric technique was used to determine the corrosion rate as a function of the mass loss of the steel exposed to mixtures of naphtha and iron naphthenate, catalyst, in both liquid and gas phases. The results indicated that the corrosion rate of the steel increased in the liquid phase when exposed to naphtha, while the presence of the catalyst caused a decrease in the reaction rate and created a protective barrier on the material due to its ability to adhere to the steel surface. Furthermore, the corrosion rate of the steel decreased over time in all cases studied due to the formation of a protective barrier from the corrosion products deposited on the steel surface. The formation of spherical hematite crystals was found to be beneficial since it relates to a more uniform and homogeneous surface that allowed for a lower corrosion rate. Furthermore, the coupon exposed to the liquid phase of the mixture without the catalyst presented dendritic and disordered growth, which is prone to the accumulation of contaminants and corrosive agents can accelerate corrosion. Experimental setup. The parts listed correspond to 1. Fluidized sand bath, 2. Discontinuous or batch type reactor, 3. Alumina sand, 4. Mechanical stirrer, 5. Temperature controller, 6. Compressor. Results from the gravimetric analysis carried out under the standards of ASTM G103. The measurement of the corrosion rate of API P110 carbon steel exposed to naphtha and a mixture of naphtha and 6% iron naphthenate in phase was carried out. Liquid and gas phase. The corrosion rate was measured in millimeters per year and the results are presented in the figure. It can be observed that the corrosion rate is higher in the liquid phase compared to the gas phase for both the injection of naphtha and for the injection of naphtha and iron naphthenate used as catalyst. Furthermore, the presence of the catalyst has a minimal effect on the corrosion rate of the steel in contact with the liquid phase, while in the gas phase, the catalyst has had a significant effect on the decrease in the corrosion rate when compared to injection of naphtha. These results suggest that the corrosion of API P110 carbon steel is more aggressive in the liquid phase and that the addition of the catalyst seems to have a protective effect on corrosion in the gas phase. Regarding the results corresponding to a higher corrosion rate in a liquid contact phase, this may be due to the fact that in the liquid phase, the ions found in the solution can come into direct contact with the surface of the material, increasing the probability that the reactions corrode the steel, while in the gas phase, the molecules are more dispersed, decreasing the speed at which corrosion occurs. Regarding the effect of the presence of iron naphthenate, used as a catalyst, on the decrease in the corrosion rate of steel. This is due to its adsorption on the surface of the steel to form a protective layer that acts as a barrier against corrosion, avoiding the degradation of steel. In addition, the iron naphthenate layer can also react with ions present in the environment to form less aggressive compounds that do not damage the surface of the material. However, in the liquid phase, the catalyst can increase the corrosion rate by increasing the concentration of metal ions in the solution and facilitating electrochemical reactions. Regarding the corrosion rate as a function of time, the figure shows the corrosion rate in millimeters per year for the steel in contact with the liquid phase of the naphtha and the mixture between naphtha and the catalyst and the steel in contact with the gas phase of naphtha and the mixture between naphtha and the catalyst for a time of 5, 33, 66 and 120 hours, and it can be observed that as the time increases, the corrosion rate decreases. This process can occur due to different factors such as the layer that is generated of corrosion products on the surface of the material can act as an additional protective barrier against corrosion. Since it is formed through the chemical reactions that the steel undergoes with the corrosive environment and can be thicker and more effective as the exposure time increases. Another factor is that the corrosive medium can become less aggressive over time due to the depletion of corrosive ions or the reduction of oxygen in the solution, which can contribute to the decrease in corrosion rate over time. Through SEM and EDS techniques, the formation of corrosion products was visualized for both conventional and catalytic steam injection on the API P110 steel coupons. The formation of spherical magnetite crystals was evident, which is related to a regular shape and soft edges that allow a more uniform and homogeneous surface, proving beneficial, since it was observed that on this coupon the corrosion rate was lower. While on the coupon exposed to the liquid phase of the mixture without the catalyst, there was a dendritic and disordered growth, which is prone to the accumulation of contaminants and corrosive agents that are involved in the steam injection processes. Magnetite had higher concentrations in the coupons exposed to the mixture without the catalyst, indicating that the presence of iron naphthenate positively affected the appearance of different corrosion products, generating a protective film on the steel. Conclusions: the effect of steam injection on API P110 steel with naphtha and iron naphthenate as a catalyst results in an increased corrosion rate in the liquid phase. This is likely due to an increased probability of reactions that generate corrosion when the material is in contact with the liquid. Conversely, in all gas phases, the corrosion rate was lower because, under operating conditions, the crude oil does not vaporize in significant quantities, minimizing contact with the coupons exposed to this phase. The presence of the catalyst, regardless of the contact phase, caused the reaction rate to decrease due to its ability to act as a precursor for magnetite formation. The formation of magnetite reduces the number of ions available for producing other corrosive products on the material. Additionally, the corrosion rate of the steel decreased over time for all liquid phases. This behavior can be explained by the deposition of magnetite on the surface of the steel during the initial hours of exposure, which likely inhibits the corrosion process.